Hello everyone, I'm Seb Bhatti and welcome to AI Tools Research Channel, where we provide knowledge on AI technology and the tools that are being created, such as ChatGPT, DALL-E, BARD, Stable Diffusion, and so many others. In this video, I'll explain how artificial intelligence really works and go into detail what's going on behind these applications. So first, you've probably heard from some famous and credible people that artificial intelligence will take over the world and it will be the end of humanity. And is this a sensible warning of things to come, or is this just an alarmist overreaction to technology that most people don't fully understand as yet? It is just normal for people to be scared of a technology that is unknown. So in this video, I'm going to get into some detail about what is really going on behind the scenes by explaining how artificial neural networks work. These networks are at the heart of AI. I'm hoping you'll become more aware and will be more able to understand just how the AI mind works, how AI actually performs the tasks that it is assigned to do. So what is an artificial neural network? Basically, an artificial neural network at its core is just a mathematical equation. It's no more and no less. A powerful neural network is typically very complex and has very complex math equations. The term neural network comes from its analogy to the network, to the mind, or human neural network in our body. Human brains have around 86 billion neurons. These neurons are what gave us the ability to do anything. They send the signal to the various parts of our body to act, and they also send signals to other parts of our brain that enable us to think and make decisions as humans do. Neurons in neural networks are parallel to what the human brain neural networks do, and that's why the nomenclature is similar. One thing you must know, and that is the neurons in human brain are much more complex and advanced than neurons in an artificial neural network. Artificial neurons do not work exactly the same way as the biological neurons do. Therefore, the analogy with artificial neurons should be limited to the basic network structure as it applies to the way that they're both networked, not the way that they fully function. In artificial neural networks, we connect multiple neurons together and form a neural network, which we can then train to perform a task. When you hear the term pre-trained model, that is essentially what has happened. The neurons in the artificial neural network connect and pass messages forward to the neurons in the next layer in the network and the next, and so forth, so on and so forth, until the entire network has been trained using terabits of data. This is similar to the biological neuron network in our brain, which also connect and pass messages forward to other neurons. So you can see why it makes some sense to draw this comparison of our brain, which is the biological neural network, and the artificial neural network. A biological neuron has a cell body with a nucleus. This is the core of the neuron where the processing takes place. Around this cell body, there are dendrites, which are the ones that receive signal. They are the signal receivers. They take in the inputs, which the cell body then processes. On the other hand, on the other end, there is an axon, which ends with the terminal axons that can pass on a signal to the dendrites of the next neuron. In a similar way, a neuron in a neural network in a computer processor, which is essentially a mathematical function, receives some input and has some parameters. The function takes an input and processes the input. It creates an output which can be passed along to the next neuron. Input is analogous to dendrites and the output is analogous to terminal axons. The function in the neural networks is like the cell body. Like neurons in the brain, artificial neurons can also be connected to each other via synapses. These are called synaptic connections. This is what a neural network is. It's just neurons connected with each other, receiving inputs and passing along outputs in a complex network. While an individual neuron can be simple and might not do anything too impressive, it is the networking of neurons that makes them so powerful. And the network is the core of the artificial intelligence systems. So how do these neurons work? And how do the neural network work in an artificial neural network system? Well, the essence of an artificial neuron is nothing but this simple equation where X is the input, W is the weight, B is a bias term, and the result or output is Zx. What does that mean? Essentially, an input X is being modified by multiplying with a weight, and then a bias is added to it in order to get a result or output. This allows the artificial intelligence system to map the input value X to some preferred output value Zx. So how are W and B determined, which is the weight and the bias? This is where training comes in. We have to train the parameters W and B into the AI systems such that the input can be modified into the most appropriate or correct output. So how is the training done? Let's do a simple example so that you can get an idea and a feel for what is really going on. Let's say you have a $5 bill. You are trying to determine if you can afford to buy a cup of coffee. The cost of the coffee is $3. So the inputs are $5, representing the money that you have, $3 for the cost of coffee, and the question is, can I afford this? You know the answer should be yes, or the output should be yes, and you're trying to train the system to give you a yes result. Initially, the system may choose an arbitrary value for the weight and bias. You enter the inputs and see what the output is. If the output is no, the system adjusts the weight and bias and keeps iterating until the correct answer yes is given in the output. Then you change the input to $2 and repeat this process again. You know the answer now should be no this time. So if the output is yes, then the system adjusts its weight and bias again until the output is arrived at no. Similarly, the inputs are changed over many iterations until the system output gives the correct answer over a variety of inputs. This is what training a model is. It's all about doing the iterations over and over again until you receive the desired output. Note that when we have multiple inputs, the function Zx representing the neuron is modified to be a sum as shown like this in the diagram. If you think about how our mind works, we sort of do the same thing. We take in all the inputs and we process this with the numbers and the math that we have learned over time and the math that we understand. With this, we figure out what we can afford and what we can't. Essentially, this is what a neural network can do as well, but just in a more explicit way using purely mathematics. Now let's examine how non-linearity is built into artificial neural networks. There's a problem with our equation that we just covered. The case just shown is a very simple yes or no output. Our function Zx, which is a simple linear equation, can provide the correct output. But what happens when the boundary conditions are not linear? When the output cannot be simple as a clear-cut yes or a no? For example, what if you are financing an expensive car for a customer at a bank and want to use an AI system to determine how much money you can lend a particular customer. In this case, many inputs would be needed and taken into account. Things like the person's income, their driving record, their work history, economic conditions, the terms of the loan, interest rates, amount of cash deposit, and a host of other factors. In this case, the output would not have such a distinct linear boundary. The output might look more like the chart on the right. A problem like this is solved by using a mathematical trick which is called an activation function. The activation function represents or is represented by A in this formula, and it's a mathematical function we apply to our output Zx. There are different choices for an activation function, but a good example is the sigmoid function. A sigmoid function is a mathematical function having a characteristic S-shaped curve, also called a sigmoid curve. It is bounded, differentiable, real function that is defined for all real input values and has a non-negative derivative at each point and exactly one inflection point. An example of a sigmoid function is the following. This mathematical treatment allows for a greater variability in the decision boundary by introducing non-linearity to the linear formula Zx. The following images show how a linear decision boundary can be modified for far more complex decision making. And with the addition of an activation function, our flowchart is modified to look more like this, where the activation function, sigmoid function in this case, is added as additional step in the process before we get a final result. So with an appropriate activation function, there is nothing stopping from AI from answering much more complex questions. Keep in mind that with a single neuron, we can only do so much. We can't do a lot, and you need more neurons to account for the complexity of deciding. For example, how much money to loan to a customer to buy a certain car. We used a single neuron to give you a general understanding, since you can see the fairly simple math behind it. But it's not complex enough to do much by itself beyond this. Even with the power of non-linearity activation functions, the combination of several neurons that form that we might call a neural network is very complex, and that is really where the power lies. So when we make complex networks with thousands and millions of neurons that are used in programs like Chat GPT from OpenAI or AI Bard from Google that was just released, we can obtain some incredible results. If you probably have not noticed already, if you've used any of these apps and found them interesting, it is because they have hundreds of layers and millions of neurons and parameters. And now back to what some people fear most about neural networks. How artificial intelligence can be scary, and why. When we talk about training a neural network to obtain certain known results, the simple case was the example of whether we could afford to buy a cup of coffee or not. And in such a case, there is not much processing that needs to happen in these various nodes. But for more complex results, such as how much money can be loaned to a customer for a car or other complicated demands, the adjustments that the system makes in the training process is a bit tricky and is hidden in what we can call a black box. And what do we mean by this black box? When we train the system using known inputs and known outputs, we are having the system self-adjust its internal networking results from the various nodes to match what the known result should be. This is, as I stated earlier, is called the training process or training the model. But how exactly the network adjusts the various layers of intermediate outputs to achieve the final output we may want is not really known. In other words, we don't know how the system is adjusting all the intermediate layers or the middle layers that are not the input or output layer. The input and output layers are known, but the stuff inside is not. And so the intermediate layers of neurons, we can call them hidden layers. The hidden layers are, that as I mentioned earlier, is that black box. We don't really know what these various layers are doing. They're performing some transformation of data which we don't understand. This is not to say that we can't find the calculated result from any particular node. We can, because the nodes are just doing mathematics. But the result will not make any sense to us. It would just appear as some arbitrary number which the network has determined to be a suitable intermediate in order to correctly obtain the final result in the output layer. It is the combination of numbers in the various individual nodes of the hidden layers in the network that result in the power of that result in the real power of AI. So we have this huge black box in the middle which does complex transformations by stitching together the simple linear equation with an activation function to create complex, highly nonlinear output which maps the given inputs to that output. Some people consider this hidden or unknown processing the really scary problem, because they say since the system is doing things we don't understand, it could start to do things on its own and pose a threat to eventually humanity. This argument is unconvincing because these networks are doing only what they are trained to. They're just doing math. This is not to say that they couldn't be trained to behave in more complex ways in the future. But with what we know today, there is no way these networks can do anything that they're not trained to do in their own way. And of course, an evil person could train an AI to do bad things, and this is what we have to watch for. But how is this any different than evil people and hackers we have today that are using computers to do bad things? No AI technology based on neural networks today could become something like the Skynet that you saw in the Terminator movies or those fictional movies that suddenly becomes conscious and threatens mankind. In conclusion, what is the real threat of AI? We think the real threat of AI is in its power to do things that humans do today, and thus potentially eliminate jobs. This is the main threat, and this is the main thing we need to contend with today. And that's going to happen whether we like it or not. AI might eliminate some jobs, but will also continue to help to do other jobs better, and as well as create many new jobs. But it's unlikely to end humanity, at least until we humans have a mind that is functioning and is rational. Humans may use AI as a technology as we use any other technology to destroy each other much before AI can figure out to destroy us. Thank you very much for watching the AI Tools Research channel. We'll bring you much more interesting stuff in the future, so stay tuned.